Hey class, today's online lecture is on information processing. So as we're talking about information processing, I want to ask you, what do you do when a yellow light appears? Do you speed up? Do you slow down? All of this has to do with our reaction time. Reaction time is defined as the time between the presentation of a stimulus and the initiation of movement. So when we see that yellow light, we have this input stimulus. Then we have this processing within our nervous system, and then it's our output as to whether or not we are going to speed up and run that light, or we're going to slow down and stop. Now the problem is that the nervous system processes are not directly observable. So the solution is that we design experiments that are dependent on different phases of information processing. So the reaction time is the measurement of movement preparation, and it has some unique properties. So reaction time is the time required for a person to prepare and begin a movement. Then we also have our movement time, which is the time between the initiation of movement and its completion. When we add these together, we get a response time. So reaction time, movement time are generally considered to be independent. One does not predict the other, and they measure different aspects of performance. So in order to measure response time, we need a stimulus and we need a timing device. For example, think of it, if you begin with your hand resting on a sensor, a light comes on, which would be like a go signal. The time from the light coming on to when your hand leaves the sensor would be reaction time. Time from when the hand leaves one sensor and hits another is movement time. So kind of think of a sprinter, like 3, 2, 1, go, and then when they end, their reaction time and then their movement time, beginning and end. So usually we have kind of this pre-warning period of like getting ready for a signal to occur. Then we have our reaction time. Then we have the initiation of the response. So reaction time, think we're kind of like planning it. And then we finally have our movement time where we're actually doing it. And then again, adding those together from start to end is going to be our response time. So certain reaction time situations, we have a simple reaction time where it's one signal, one response. Maybe the sprinter hears the fire of the gun, they go, and then they finish the race. There's a go, no-go response. Think of a baseball batter. A baseball batter has very limited time to decide whether or not they're going to swing the baseball bat. So within their brain, they're saying go, 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 and then if they see it outside the strike zone, they quickly react and say no go. Then we have choice reaction time, which would be multiple signals, each with different responses. And we got to choose the traffic signal. Are we going to speed up or are we going to slow down? Then discrimination reaction time. You have multiple signals, but you have one response. This would be like a jogger avoiding obstacles. There's a pole in the middle of the sidewalk. The only response is to avoid that obstacle. So now reaction time can be further divided into two components, the premotor and motor. Premotor being the time from stimulus to beginning of EMG activity. So EMG, when we first start to elicit some muscular activity, measures receipt, processing, and transmission of the information. Then we have our motor response, time from the onset of EMG activity to the initiation of the movement. And remember, we talked a little bit about voluntary muscular contraction, how there's a little bit of a lag period there. So here's our premotor area. Then we have the initiation of muscle activity. And then, again, we'll have electrical signals that occur prior to the initiation of movement. So we see our fore period kind of like our getting ready to go. We're kind of anticipating it, right? Then we have our premotor reaction time followed by our motor reaction time. And then we have our movement time in which our skeletal muscle is actually contracting, causing movement, and then until the response ends. So information processing can either be serial or parallel. Serial would be like successive stages in an assembly line down the row, or parallel, they could be happening at the same time but in different places. So the model that we look at is we have this input, And within that nervous system for processing, we have to have stimulus identification, response selection, and response programming. So stimulus ID would be we need to sense that a stimulus has occurred and identify what it is. And there are several steps. So we sense that something's changed in the environment. We now take that stimulus, transform it into a neurological impulse, and then the stimulus must then be recognized or matched with a previous experience. And so we now perceive that stimulus. And we can improve this through stimulus clarity, making an image sharper, stimulus intensity, something brighter or louder, okay, and stimulus modality, so the way we react to auditory stimulus faster than visual stimulus. And we'll see this example with the batter's eye to enhance stimulus identification. The batter's eye is this big green sheet out in the back of center field, which allows the batter to identify or see the baseball a lot clearer. And it's a very complex task of identifying a stimulus, so like recognizing a face or shape, identifying a strike versus a ball in baseball, just giving you the idea that it's stimulus ID. We kind of take it a little bit for granted. It's like, oh, we know what that is, but there's a lot of complexity that goes into all of that in previous experiences. Now, response selection. How are we going to respond? So an individual must decide which action to take. Okay, it can be one of multiple choices or no action at all. And we can increase or decrease reaction time. So move slower, which would be increasing reaction time, or move faster, which would be decreasing reaction time, by influencing response selection. So increasing the number of stimulus response options. Okay, if there's more options, we're going to react a lot slower. And then stimulus response compatibility, we want to have a response that's compatible to the stimulus. And an example of like a poor stimulus response capability would be like hearing a noise in your right ear and raising your left arm. Okay, we didn't respond correctly to that. And this leads us to Hicks' law, which the relationship between reaction time and the number of choices, they show a curved relationship between the number of choices and reaction time, meaning an increase in reaction time between 1 and 2 choices we see is approximately 150 milliseconds, and between 9 and 10 choices is approximately 3 milliseconds. There's a little bit more detail in that we'll cover in the next couple slides, but the idea here is that with more choices that are kind of similar, that we have an idea, all these choices, we've already started to eliminate things, so the choice is starting to become a little bit faster. Until some of those choices, if those choices lead to uncertainty, then we start to have some issues. So here's kind of what the graph looks like. And then what we see is that Hicks' law, reaction time increases logarithmically as the number of choices increases. This means that the relationship is linear when plotted against bits of information. Okay, so when we talk about log, so our brains process information like computers. So if we have 1 bit of information, okay, that would be like having 2 choices. 2 bits, 4 choices, 3 bits, 8 choices. The more bits of information, the more choices there are. So a plot of reaction time versus bits of information is linear. So the more choices that we have, okay, that are uncertain choices, right, it's going to lead to an increased reaction time. So information theory can be thought of as reducing the amount of uncertainty in a situation. So reaction time is increased by a constant amount every time the uncertainty is doubled. Okay, increasing the information by 1 bit doubles the uncertainty of the response. So compatibility, we mentioned about hearing a stimulus in our right ear, raising our left arm. So reaction time decreases as the relationship between stimulus and response improves. So we see on the left we have a poor stimulus response compatibility. On the right we see we have a good stimulus response compatibility. The Stroop effect, this is a very, very difficult one. Still sticking with stimulus response capability. So we must say the color of ink of a word. So if we see blue and it spells blue, we'll have a fast reaction time. If we see the word black, but we have to say blue, we're probably going to have a slow reaction time, again, because there's that uncertainty and it's going to take us a little bit longer to identify and then process, oh, the word says black, but we have to say blue. And then here's just a little example of design of a stove for compatibility. Some of us should not cook. And now leading us to our last part is response programming. So the individual must prepare for and initiate an actual response. So a motor program is retrieved, it's prepared, and it's readied for action. So we can increase and decrease reaction time by influencing this response programming phase. Example would be the complexity of the resulting movement. So we can have a fast or slow reaction time depending on how complex of a movement that we have programmed. So the performer can organize and initiate an action only after having identified the stimulus and selected a response. So the performer now must translate this abstract idea into a set of muscular actions that will achieve the desired action. So RT increases as the complexity of the task increases as well. It's related to the number of movement parts. So more than one movement to complete a skill or more than one joint. It's also related to movement accuracy requirements. So reaction time increases, meaning we move slower, as precision requirements of the task increase. Reaction time increases as the size of the target decreases, thereby increasing the accuracy demands of the movement. Then we have movement duration. As movement duration increases, reaction time also increases. So the effect of movement complexity on reaction time occurs both when a person knows in advance what movement will be made and when the choice of movement is not known until it is indicated by the stimulus. So other factors that might influence reaction time: pre-cueing. So the probability of pre-cue correctness is important to reaction time. We can think this of a basketball defender, and there's kind of a cost-benefit trade-off. Is it worth the risk to guess? So it's kind of an anticipatory response. So when evaluating reaction time, we cannot just look at it in a way where the stimulus information is presented with an unrealistic expectation that the stimulus would not be anticipated. So many of the stimuli that we respond to in our daily activities are predictable, so we can view patterns, so on and so forth. And so if we anticipate wrong, it can result in an error, but we then learn and reprogram that. We mentioned the 4 period earlier, kind of getting ready to go. So often it's a warning signal given before a stimulus. Ready, set, go. If the 4 period is of constant length, then reaction time will decrease. But if we, kind of say 3, 2, 1, it's going to mess up our reaction time of when we decide to actually go. And then repetition of movement, the more reaction time decreases as we have an increase in repetition. So to kind of give an example of the latency periods that we have, so if we're responding to 2 different successive signals with different responses to each, reaction time will increase for the second movement. So serial processing limitations. And then we have this psychological refractory period, which is delay between successive movements. Cannot select the second movement until the first is completed. So this would be like the basketball fake of breaking ankles. There's several stimulus that enter, and we have to complete one before we complete another. So if we anticipate going one way, but then see that the athlete is going the other way, we have to complete our first movement before we actually start our second movement. So in terms of practical application, how do you think RT would be affected in the following situations? I'll let you guys think of that. Which stage in the information processing model is likely to be affected? So if we think of a cell phone, slows reaction time. Age, reaction time decreases as well, then increases slowly to about 70. So also, and then